Well, welcome back. I apologize for the late start. I was on a phone call with the VA, which is like bureaucracy got crazy. Anyway, I got all that information. Okay, I haven't had a chance to finish grading the exam. I have about 5 or 6 questions that I have to grade. I'll get that graded tonight. Has anybody been having any problems with the Canvas program itself as far as our particular course freezing up? Uh, you click on any of the links and it just freezes up and then an error pops up.
Yeah, I had that problem with Canvas, and it was every time I tried to click on something, it would kick me off of the internet. So I had to mess with my internet settings on my computer to kind of fix that. I had to kill a couple of programs.
Oh, okay. Because I've been having the same issue. I think it's a Canvas thing. I did talk to tech support because I can access all my other classes and all the other information. It doesn't hang up. It's just ours itself. So I don't know if it's our class itself. If you're not having any problems, then good to go. But I know I couldn't even access the grade books to put grades in there. So hopefully I can find a workaround and they'll get back to me today and I can input that information. Okay. So yeah, contact tech support if you are having any challenges. All right, so we have finished chapter 8. Any questions? Any other questions, comments, concerns? All right, we had finished chapter 8, and I'm going to add some additional information to this. These files that I have are given to you in the nomenclature module, okay? So I would start, speaking of the nomenclature exam, go in there, start taking, trying taking the exam. Like I said, there's only 20 questions. You can't. There's nothing to lose. I know you're just learning it, but at least you'll get an idea of where you need to go based on how you're doing. Okay. And remember that particular exam is worth 10% overall. And could play a factor with respect to your grade, especially if you're on the border, okay? It can push you up or it can keep you from moving up to the next grade scale. Or it can push you down or keep you down, I should say. All right, so yeah, do as much of those as you can. So some of the files that I share with you is this one, for example. It's called a list of some other polyatomic ions. These, by all means, is not an exhaustive list, but there's some additional ones that may show up in the nomenclature exam. But just to give you an idea of all these polyatomic ions that we have access to that are there that we know exist. Here are some positive cations that normally will be metals. If you look at them, they're all metals, okay? And we look at the negative anions, and then we have a lot of charged poly ions that have a multiple of different oxidation numbers, okay? Because for example, we got iron with a +3 here, but it could be iron with a +2. We got copper +2, etc. Here's the iron with a +2. This used to be the old naming, the ferrous, the ferric, naming that kind of doing away with because it's kind of ambiguous. And that's why we use the Roman numerals now to depict the actual charge. This is carbide. This is comes up a lot in the nomenclature exam. Carbide, which is just carbon, which in this case, carbon being in group 4 has the capability, as I mentioned, it's on the fence. It can lose all 4 electrons, all 4 valence electrons, but it can also has room for 4, so it can pick up 4 electrons. And so you'll see it here with the -4 charge because it picked up 4 electrons. And then we call that the carbide. Another one that I shared with you is called nomenclature of acids. For example, if you get the chloride ion, okay, and acids, which we're going to talk about in this chapter, acids and bases, what denotes an acid is first of all, one, acids come from covalent compounds. And what happens is that I explained yesterday in lab is normally covalent compounds do not dissociate. They stay intact when we put them in an aqueous solution. It is only acids that when we place them and dissolve them in an aqueous solution that they dissociate, they break apart. And in doing so, in breaking apart, if you will, they produce what is called a proton, okay, which is basically hydrogen with a plus charge. Now, keep in mind, hydrogen, if we look at the Lewis dot structure for the hydrogen atom, has one valence electron, and that's why it sits in group 1A. One valence electron, same attribute as all the other metals are in group 1. Okay, and it's placed there because hydrogen also has the capability of losing that one electron. So you can see here, here's hydrogen with its one valence electron, and when you lose that electron, it becomes an H plus, and it has its own unique name. We call that a proton. And that is what makes a moiety, a species, an acid when a covalent compound is dissolved in water and it dissociates and it produces a proton and makes it an acid. Okay. Now, an additional side note here is that hydrogen atom, remember its electron is, the electron configuration here is 1s1. So it has room for one more electron. So hydrogen atom has the capability of picking up one more electron because it does feel that s orbital now it's 1s2. And that makes it a negative charge because it picked up an electron, just like the ones in group 7. Okay. There's a question. I just saw your note here, Teresa. Okay. If you're having trouble putting in, no worries about that. If you're having trouble putting in the superscript and subscript, then by all means use that little caret symbol. That would work and function properly. Now that I know for sure what you're trying to write. Okay, so when it picks up an acid, an electron, it has a negative charge, just like the species in group 7, all the halides, they can pick up one electron and end up with a negative charge. And sometimes some periodic tables actually put the hydrogen not only in group 1, because it can lose that electron and end up with a plus charge like all the other metals, or it's placed in group 7 because it can pick up an electron and have a negative charge, just like the halides, like the fluoride, the chlorides. And in fact, when it does that, this has its own little name. We call that a hydride. Just like chlorine becomes chloride. Sorry, my pen is not doing its thing. Hydride. Let me try it again. Hydraide. Oh, that's crazy. Crazy handwriting. Okay, hydride. Hydraide. That's when it picks up, hydrogen atom picks up form. Anyway, to go back to producing an acid, it produces a proton, and we'll have much more in that next chapter. Okay, clear this up. And so what happens here, we have HCl, okay, listed here. We call it hydrochloric acid. Here's the interesting part about nomenclature. Very interesting, kind of ambiguous, okay? And when it comes to acids, this is called, when we put the chloride back on the hydrogen, we generate HCl, as it's called hydrogen chloride. If it is an aqueous solution, okay? If it's not, because HCl is really a gas, okay, is called hydrogen chloride. Okay, hydrogen chloride when it's a gas and it's not an aqueous solution. But it's called a hydrochloric acid if it's an aqueous solution. Okay, most of the time, if you don't see the AQ, then assume it's the gas, and its full name is hydrogen chloride. I've been trying to fix that in nomenclature exam because they do treat it as hydrogen chloride, but I do give credit if you write down hydrochloric acid. So I would just want you to know the difference between the two. Okay. All right, so you can do that with any of you got fluoride, chloride, bromide, put the hydrogen back on. Now you have hydrogen bromic acid, for example, so on and so forth. Now, we also have other acids that we call the oxo acids, and I'm going to talk a lot about this. Now, in the polyatomic ion table, you'll see we have the nitrate ion and the nitrite ion. These are nitrogens with oxygens bonded to them, and they have a charge, okay? Now, where these came from originally was they came from acid. So that negative charge to make it the ion occurred because it reacted with the base. And again, I kind of introduced this subject a little bit early, but you'll see how that comes into play here, that to generate a nitrate ion, we actually start off with nitric acid, okay? And notice that HNO3 is neutral. Well, it's an acid. Notice it's covalent. And when it goes in solution, it will produce a proton, making an acid. Now, you may ask the question, well, how do I know by looking at it that I have an acid? Well, here's the deal. 99% of the time, okay? 99% of the time when they write the formula, guess what? You're going to have the hydrogen written first. Notice in all these cases, you got the hydrogen written first, okay? In the other examples, you're going to have the hydrogen written first. That is a good indication that you're dealing with the acid. The only exception is, H2O. That's a water. Water is not an acid, okay, but it does have hydrogen written first. That's why I say 99% of the time, at least for Chem 130, if hydrogen's first followed by whatever, good indication you are dealing with an acid, especially if what follows is more nonmetals, okay? So hydrogen nonmetal, chloride nonmetal, boom, I have an acid because hydrogen is written first. So going back to here, if you take the nitrate ions and the nitrite ions and you put the hydrogen back on, because that's where it came from. Originally came nitric acid, is HNO3, and nitrous acid if it is HNO2, okay? All right, now we're gonna have a whole PowerPoint on the next topics where we talk about these guys. For example, you'll see that looks pretty complicated here, okay? Well, it can be, but there is a systematic approach to this, okay? Now, what we have here are these anions, polyatomic anions, okay? And thing to remember is this one here that is called the ATE, the 8 is our base name. See, the nitrate is our base name. We got the chlorate, okay? That's the base name. Now, if we add an oxygen to that system, we end up with perchlorate. Okay? Here's the perchlorate as we go up and add an oxygen. If we take out an oxygen, just like the other case, where we have nitrate goes to nitrite, well, the same thing happens here. We go from 8 to 8. if we continue to remove an oxygen, then we add the term, the prefix hypo, and then ite, okay? And eventually, you are dealing with the chloride. The ion, so the halogen, the chloride itself. Putting one oxygen becomes hypochlorite, two oxygens, chlorite, three oxygens, chlorate, and perchlorate for four, okay? Question been asked, are there more? Can we have five? Well, to our knowledge at this point, it's not been isolated. It doesn't mean it's not out there. To our knowledge, no at this time, but until more information is found, no. Okay, now, all these polyatomic ions, if you put the hydrogen back on, notice there's a negative one, so they all are going to have one hydrogen. Okay, so you take the perchlorate ion, put the hydrogen back on, all right? You remove the 8 and the ion and substitute that with ic and acid. So now you have perchloric acid, okay? Look at the chlorate ion, the second entity, put the hydrogen back on. This is the one with 3 oxygens. Now it becomes chloric acid. The chlorite becomes chlorus, ite goes to OUS, okay? And then since you still have ITE, you keep the OUS, but because you have a hypo in front, it comes, the last entry is hypochlorous acid, okay? And then of course you got chloride, and if I were to put hydrogen back on the chloride to have HCl, then of course I would have hydrochloric acid, okay? Hydro, not hypo, but hydrochloric acid. And this general trend, the way we did it, is true for any other. If the bromide was instead of the chloride, if any of the other halogens were being utilized there, we would go through the same thing. Okay, they all had the same sequence of naming, starting with the ion and then progressing to the acid, or vice versa. Okay. Those are you call it binary acids. These are the fluoride, the chloride, the bromide, the iodide ion that has hydrogen placed back up. Okay, and we just simply put the hydro, and instead of, we take the term fluoride, for example, remove the IDE, add hydro, and add ic acid. So we have hydrofluoric acid. Okay, hydrofluoric acid. And to show you, if we have fluoride, okay, just the F ion, okay, fluoride goes to hydrofluoric acid, chloride goes to hydrochloric acid, etc., etc. Okay. Now we have the oxyacids we talk about, and I have a whole PowerPoint dealing with the oxyacids. There's a limited number of them. There's not a whole bunch of them. Okay, and I'll get to that here in a bit. And then we have organic acids. Now, these are, we're only going to be dealing with acetic acid, aka vinegar. But FYI, formic acid, if you ever have gotten bitten by red ants, that's what you got injected into your body, formic acid. Very painful, and for some people, it can be very, very bad. Okay, so anyway, acetic acid, aka vinegar, okay, and they are organic acids, and they will, unlike the other acids where we got hydrogen written first, we don't always have the hydrogen written first. Sometimes they're written on the far right for organic acids, but Not to worry, we're just going to be dealing with, if we are going to deal with any acids, organic acids, it would be the acetic acid. When it reacts with the base, guess what? You make the acetate ion, which is in your table with polyatomic ions. All right. Let's see, let me go now to, come on. This on there is another, it is a Word document with some information. Now, the oxy acids that we're going to work with for a minute only deal with these elements. They're in the upper right side of the periodic table. So boron, carbon, nitrogen, then everybody in group 4 down to stannous, SN, then nitrogen down. Oxygen and fluoride are not involved. Oxygen will be involved, obviously, but not as a standalone acid. Sulfur, selenium, and beryllium, chloride, bromide, and iodide, just those, okay? Now, the single ions, obviously, they had the suffix IDE, so boride, carbide, siliconide, nitride, phosphide, etc. Okay, now this will make more sense in a minute with the polyatomic ion. So basically, this is the parent polyoxy ions. The parent are the ones that have the name, the suffix ate, okay, ATE. And from there, we're going to go either to the ite or hyphals or whatever. We're going to lose or gain oxygen. So for the ones in blue, they always start off with 3 oxygens, okay? And that is their overall charge. So the BO3, for example, has a -3. The carbonate, which we're familiar with, is part of the polyatomic ions in the table, 3 oxygens, and has a -2. And we're also familiar with the NO3, which is the nitrate, excuse me, with a -1, okay? The other ones, for example, SI, GE, SN, stannous, well, they start off, the H start off with 4 oxygens. So all of them you can see have 4 oxygens. Furthermore, they all have a -4 charge. Okay? The next group in, starting with phosphorus, also has 4 oxygens as the parent polyatomic ion. Okay? But the difference is they have a -3 charge. And then the next group in, I keep them all in yellow because everyone in yellow starts off as the parent ion, polyatomic ion, with 4 oxygens. Where they differ is the overall charge, going from -4, -3, -2, okay? And then the ones in green, the halides, the H's all start off with 3 oxygens bonded to them, but overall they have a -1 charge, okay? And this is the base name, the base polyatomic ion, all of the H's, so here we have carbonate and so forth, but we'll give you some names here in a bit. Now, where do we go from here? Well, let's take the example in yellow, the carbonate. And this will be true for any of the base H polyatomic ions that we just talked about on that table, okay? So any of those starting with the 8. Now, if you add an oxygen to the 8, then it becomes name-wise per carbonate in the case of the carbonate, okay? So it has 4 oxygens, CO4. Now, the likelihood of that occurring is pretty low, but just for demonstration purposes, we're going to assume that thing exists, okay? And that's true for all of them, for our educational purposes. All right, now if we take the carbonate and we subtract or remove an oxygen, then we have carbonate, okay? And then if we remove one more oxygen, then we have the hypocarbonite. And obviously, if we've removed the last oxygen, then we have carbide or carbon, either one. Okay, carbon. All right, so the parent names for the ones we just talked about right here in blue, yellow, and green is given here. You got the boronate, carbonate, nitrate, etc. Those are the parent names. And then from there, removing or adding oxygens, you add either a per to add an oxygen, or you remove the 8 and substitute it with an ite, and then the hyponitrite when you got one oxygen. Okay. And this is just some extra sheets here to help you practice. And this was a table I was putting together of all of the different polyatomic ions that we have, going from the element itself, going to from the ion, the anion, like take nitrogen. You start off with nitrogen, okay? Obviously, nitrogen becomes nitride when it becomes the ion. And we start talking about the polyatomic oxy ions. We start adding oxygen. So NO would be called the hyponitrite. NO2 is the nitrite. NO3 in yellow is the parent name, nitrate. And if it had one more oxygen, it would be called pernitrate. Okay, all of them involve nitrogen and oxygen. We go from the element to the ion to the polyatomic ion. I did the same here with sulfur. Sulfur goes to sulfide. There isn't a SO, so it goes directly to SO2, so hyposulfite. And then 3 oxygens sulfite, 4 oxygens sulfate. Whether there exists 5 oxygens, to my knowledge, not at this point. So what I try to do is put some reality to these of what is known at this time. Okay. Okay, here's carbon. Carbon is a lot of it. You see here C2 with a -2. It's written like that, but you can also, I've also seen written as carbon with a -4 here. Okay, so either one would be acceptable. So we got carbon atom, it went to carbide, to hypocarbonite, to carbonite, to carbate, and then percarbonate. Okay, so on and so forth. So more additional information for you. So let's do this now. All right. So we have the periodic table here. Okay. And basically what I did here was let me open it up all the way. So, you had that information on the papers we went through. So let me start off just with the elements themselves. So we're talking about in blue, boron, carbon, nitrogen, just to the upper right corner of the periodic table. We don't use the fluorides and we don't use the oxygens, obviously, because oxygens would be bonded to these elements. All right, so I try to do a color coded here. So everybody in blue, well, not yet, but the boron, everybody, we had others, the boron will have a -3 charge, okay, when it becomes bonded to oxygens, a -2 for the carbons when they're bonded to oxygens, and a -1 for nitrogen when it's bonded to oxygens. Now we're starting off with the 8, the base name. Everybody here is going to be an 8, okay? -4 for the first group in yellow, -3 for the second group in yellow, -2 for the third group in yellow. That is for the overall polyatomic oxy ion. okay? And then the ones in green will all have a -1. Now, everybody in blue starts off with 3 oxygens, and that is the 8. See, borate, carbonate, nitrate, okay? Where they differ is their respective charge, overall charge. Okay, everybody in the yellow starts off with 4 oxygens. They're going to differ in the overall charge because the first group has a -4. The first group in yellow has a -4. Second group in yellow has a -3. And the third group in yellow has a -2 for their respective 8 polyoxyoxygen. And then the green all start off with 3 oxygens, okay? So everybody there has the 8 suffix with respect to their name, of which I gave you those names in the other papers, okay? I also gave you links for videos to explain all this. There are alternative people presenting this topic. Obviously, feel free to listen to them, and maybe they have a different way to have you grasp it for you. But I try to line it up as logically as possible here for you. Okay, so you can see the trends and so forth, and you can connect the dots and take this information and proceed as you need. All right, here is what I talked about. Here's the names we talked about. For the parent name, starting off with their respective maximum number of, not maximum, but the number of oxygens, which is right there. Okay, the blues have 3, the yellows all have 4, and the greens all have 3 oxygens. Okay, and there's their respective name: borate, carbonate, nitrate, orthosilicate, germanate, stannate, phosphate, arsenate, antimonate, sulfate, selenate, terylonate, chlorate, bromate, iodate. Okay, and then by removing, everybody starts off in number 3 as the parent name, and then as you add 1 oxygen, it becomes per whatever. In this case, per carbonate. You remove an oxygen, it becomes carbonate. Remove 2 oxygens, you become hypocarbonate. Okay. All right. So much for that. So yeah. Take a few minutes to read that. That will help you with respect to some of the nomenclature that pops up as far as being able to name them. There are not a lot of them, but it's maybe a handful of them that pop up to help you out. That information will help you out. Okay. Any questions? All right. Well, if we don't have any questions, then we continue. Okay. Acids and bases. Okay. I've introduced this topic already, but we're going to go into a little more detail. Okay, as I explained earlier, hydrogen has a capability of losing that valence electrons. It's only got 1 electron, so it very rarely can lose that electron. And what happens is, in losing the electron, it produces an H+ ion that has its own little name, and then we call that a proton. Okay, now we're going to get 2 definitions of an acid, and 2 different scientists have come up with definitions for an acid and a base. But in both cases, with respect to an acid, the definition is essentially the same. Basically, is this: anything that produces a proton when dissolved in an aqueous system, okay, is considered an acid. And so normally anything that's an acid, we got vinegar, sour, a lot of the citrus are sour, lemon, okay, very sour in taste, can be corrosive, very corrosive. The acidity can attack a lot of things. Now, what we have is paper, litmus paper specifically, and there's two types. There's blue and red. Now, what it is with respect to this paper is hold on one second. Maybe stop sharing for a moment. Nope. Stop for a second. Something is acting up on my end. I guess not. All right. This litmus paper, it's either going to be one or the other. For example, blue litmus paper, if you put the blue litmus paper in solution, it turns red. All that tells you that it is an acid. And there's degrees of acidity. We had strong acids and very weak acids. So it's not going to tell you anything like that. It's just going to say, okay, it's an acid, and that's it. Okay. So a blue litmus paper turning red implies that that solution is an acid. Now, look at this polyatomic ion. I'm sure you're familiar with it. The OH negative is the hydroxide. Okay. And one definition of a base is that anything that produces a hydroxide ion when dissolved in solution is considered a base. Okay. One definition. Now, we're going to deal mostly when we talk about acid and bases, that particular definition. But there's another definition that allows you to encompass even more chemicals that can be classified as bases. But for right now, anything that produces a hydroxide ion is considered a base. Sodium hydroxide, potassium hydroxide, ammonium hydroxide. Literally any of the metal combination, OH combination, is a base. Okay. All right. So I wouldn't taste it because it can be very harmful to your tissue. Okay. If you do taste it, it's bitter and chalky. And it feels, if you put some in your finger, you'll feel it to be soapy and slimy, and you think that's the chemical, but it's not the chemical. What is happening is the hydroxide ion has this ability to denature your tissue and break it down to form this gelatin. So that's what you're feeling, is your tissue breaking down. In fact, a lot of the cleansers, a lot of the makeup things you ladies do to your face, they are a hydroxide base or a basic solution that literally removes, skin tissue, so you can create new skin tissue. Okay, so it's not very strong base, but it is an alkaline solution. We call it alkaline. More on that in a second. Now, as I mentioned, we had two litmus papers, blue and red. In this scenario, red litmus paper will become blue in color if it is a base. Okay, so I have an acid and a base. Now, by definition, the first definition is arrhenius. Arrhenius, acid and base. And this definition goes way back for a long time. Now, what Arrhenius is saying, that any chemical that when placed in an aqueous solution dissociates, breaks apart, okay, to generate the proton and the chloride ion here in the case of HCl or hydrochloric acid, okay? So any acid that dissociates, that produces H plus is considered an acid. thing to remember, put in the back of your mind, that in this scenario, HCl totally dissociated, literally close to 100%. And so, as we were talking about conductors yesterday, it produces a lot of ions in solution, so they would be considered a very strong conductor because there's a lot of ions in solution to carry that current. Furthermore, because it produces literally all of the protons that it had to begin with, it is considered a strong acid, okay? As compared to some other acids that we're going to talk about, that when they dissociate, they don't dissociate 100%. They dissociate, it varies in 1 to 5%, or even less, a little bit more, I should say, but very little. The bulk of the material remains intact, and it does have a few ions in solution. There's not as many protons in solution as the case here. An example of that was vinegar. Vinegar is considered a weak acid because there's not that many ions in solution, okay? All right, now, with respect to Arrhenius' definition of a base, any compound, specifically, if you look at the difference between HCl and NaOH, what is the main difference between the two? Can you see that? Can you see the main difference of classification of this compound versus this compound? How can I, obviously one's an acid, one's a base, but what do I see there that makes them different, HCl different than NaOH? What do you guys think? Think in terms of chemical bond. Look at the chemical bond of HCl versus NaOH. What is the difference between the two?
HC is covalent.
You got it. That is correct. Okay, this is covalent. And NaOH?
Ionic.
You got it. Ionic. Good. Okay, so note the big difference here that when we talk about acids, we're talking about covalent compounds. And I repeat what I said before, that covalent compounds normally do not dissociate. The only covalent compound that will dissociate is an acid, like in this case here. Now, with respect to, and as I mentioned, some acids dissociate 100% and some much, much less. Well, the same is true for ionic compounds. In this scenario, due to the solubility of sodium hydroxide, due to the solubility rules that we're going to learn about, anything bonded to sodium makes it classified as sodium. Hence, literally, when we put it in water, literally 100% gets dissociated, as the case of the top one, okay? Making them both HCl a strong acid and making sodium hydroxide a strong base because they dissociate 100%. And if we had that reader, the conductivity reader, will find that both these checking the solutions would make that little LED light up bright because they're strong, okay? But one's covalent and one's ionic. And based on the solubility rules for the ionic compounds, we're going to learn that a lot of them are classified as insoluble. But even though they are insoluble, there's always a little bit going in solution. So there'll be a little bit of ions in solution that will conduct electricity. Remember, that's what causes the conductivity of a solution is ions. But even though they have a small amount, much smaller amount of ions, it will conduct electricity. And that LED wouldn't light up as bright, but it will still light up. And those are classified as weak, okay? Weak acids or weak bases. Now, something interesting to note here, that your first reaction. Now we got the proton here and the hydroxide here. Keep this in mind. Next time you take Tums, what do you think is happening? I mentioned this in class already. Okay, you take some Tums, you got acid, hydrochloric acid, in fact, HCl in your stomach. You take Tums, okay, which is a base. Okay, now you know what a base is. It's producing some OH, okay? And then after a few minutes, you start feeling a little bit better. You're not having as much acid in your stomach. And what's happening is you neutralize the acid. And this is what's happening. The proton reacts with the hydroxide, and guess what you get? H2O. Okay? So the acid and the hydroxide neutralize each other to generate water. Now you might think, well, how does that happen? Well, if we do the Lewis dot structure for hydroxide, we end up with 3 pairs of electrons on the oxygen. And the proton, remember, the proton now, its orbital is empty because it lost that electron. So that orbital is still there, but it's empty. And so it can take 2 of those electrons and generate a bond there. We end up with a bond between the hydrogen and the oxygen, and hence we generate water. Okay? So this is your first type of chemical reaction, which is the preceding chapter we're going to talk about, is chemical reactions. And this is called a neutralization reaction. A neutralization reaction is a reaction where we have an acid and a base neutralizing each other, okay? And you produce water. Now, the other takeaway that concept that you need to grasp is the following. Notice in front of hydrogen, it's understood that there's a 1 here, okay? And in front of hydroxide, it's understood to be a 1. And in front of water, it's understood to be a 1. That is what we call the stoichiometric relationship. We're going to learn a lot more about this, but it basically says that I need one molecule of hydrogen and 1 molecule of hydroxide to come together to form 1 molecule of water. Therefore, if I have 1,000,000 molecules of proton, how many molecules of hydroxide do I need? What do you think?
2.
No, think about it. No. Let's try again. Okay. I got 1 proton requiring 1 hydroxide. So if let's make the numbers a little smaller. If I have 5 protons, how many hydroxides do I need? Remember,
5.
You got it. And how many waters am I going to make?
$10?
Not quite.
Oh, no.
Think about this for a second, okay? Let's think of the proton as the frame for a unicycle. And think of the hydroxide is the tire for the unicycle. So if I have 5 tires, 5 frames, I put them together, how many assembled unicycles am I going to have?
5.
You got it, okay? You're going to have 5. And, oh, come here, mouse. 5. And so if I have 1,000,000 protons, how many hydroxides do I need? To neutralize 1,000,000 protons.
1,000,000.
You got it, okay? Which will make how many waters?
1,000,000.
You got it. Now, that information, put in long-term memory because we're going to use that when we start looking at these acid and base reactions and we try to balance them out, okay? Because we're gonna find, if you see right now, that HCl, when we put in solution, only produces one proton. But we have acids that produce 3 protons. One of those we talked about was H3PO4. When phosphoric acid goes in solution, it produces 3 protons and the phosphate ion. Okay? And if it's producing 3 protons, I need 3 hydroxides to neutralize those 3 protons. And if I'm reacting phosphoric acid with the base. And if I need 3 hydroxides, I'm going to make 3 waters. That information will help me to balance these type of reactions, because I need to learn how to put that correct coefficient in front of the reactants and in front of the products. And when I deal with acid-base reactions, the best way to balance them, and that means putting the correct coefficient in front, is to follow the proton and to follow the hydroxide. And that everything else that's involved just comes with it to help balance it. Okay. Now, why do I need to balance it? Because with those coefficients, now I can do chemical calculations, because I gotta have the correct coefficients before I can go to the next step. All right, so a little bit ahead, but that's okay, because we're gonna, all this is kind of tied in together here. Okay. All right, so by definition, Arrhenius acid, anything that produces a proton, H+, a base is anything that produces a hydroxide ion. And I can take the proton and react it with the hydroxide and then neutralize it to form water. Okay, that's called the neutralization reaction. And that's what we got right here. Okay. You have an acid, which is hydrochloric acid, HCl. Okay. And then we have a base, which is sodium hydroxide. They're going to react with each other. So a classic example is the TEM scenario here, where we got an acid, hydrochloric acid in your stomach, and you ingest some base. We're going to neutralize some of that acid. I put the arrows to tell you what happens, that the proton and hydroxide react together to form the water. And then what's left over are just simply the salts. They're not really involved in that reaction. If you're going to sit there, they're spectators and not doing anything other than balancing the charges with each other. So now the sodium and the chloride come together and you form the sodium chloride. Okay? We form a salt. Any neutralization reaction forms a salt. Now you might be tempted to say, okay, it always forms, because we're familiar with salt and sodium chloride. Well, I want you to try to get away from that thought process, because in chemistry, a salt is any combination of a metal and non-metal, which is what? What do we call that kind of compound? Metal, non-metal.
Ionic.
Ionic. So the salt is any ionic compound. So it's not necessarily sodium chloride. We think of it as sodium chloride because that's what we use every day. We put it in our food. But salts could be any metal and any non-metal coming together. Okay. The main thing is we got that proton and hydroxide neutralized to form water. Right. The coefficient here in front of everybody is a 1. This means that this particular reaction is balanced. You might think, well, what am I talking about here? Okay. Now, what we do is, to the left of the arrow, we count up all of the hydrogens. So we got a hydrogen on the hydrochloric acid and a hydrogen on the sodium hydroxide. So we have a total of 2 hydrogens on the left-hand side. All right. On the right side, we also have 2 hydrogens, but they're in the form of water. Okay. But it's still hydrogen. We got 1 chloride on the left-hand side And we have one chloride on the right-hand side. So chlorides are balanced. Mother Nature's happy. So chloride. Sodium, we got one sodium on the left-hand side and one sodium on the right-hand side. So sodium is balanced. Then we have one oxygen in the form of the hydroxide. And then we have one oxygen in the form of water. Okay. So in this particular reaction, we have a balanced chemical reaction. It's understood now that the coefficients, though there's no number there, it's understood that there's a 1. And the way I read this, I say that 1 hydrochloric acid is required to react with 1 sodium hydroxide, which will give me 1 sodium chloride and 1 molecule of water. Okay. And that's my coefficients that now I can use to do calculations, because I could have a question that says, if I have 5 grams of sodium hydroxide to begin with, and I have the correct amount of hydrochloric acid, how many grams of water am I going to generate? That is an example of a typical chemical reaction. Or it could go the other direction and say, I need to make 1,000 grams of water. How much HCl do I need to begin with? Okay, these are the type of chemical reactions that we will be doing. Okay, but we can't do them unless we balance a chemical reaction and we write it correctly. All right. And the other aspect about this chemical reaction, that reaction holds whether I do it in the lab in small scale, or whether I'm out there and I'm doing it in industrial scale where I'm working with millions of pounds of it. If for some reason I'm trying to make sodium chloride, which is not very efficient here, but if I were, those are the chemicals I need to make of, and I need to make 1,000 pounds of this large scale, this reaction holds. Okay. Now, the other definition of an acid and a base, and after the two scientists called Brownstein and Lowry, they put in their definition. Now, the advantage of this definition is simply that it opened up, with respect to bases, how we can get more chemicals were classified as bases. Remember, the Arrhenius definition, the criteria was to be a base, you got to produce hydroxide. While Brownstein Lowry has nothing to do with hydroxide at all. Okay. In both cases, they have something to do with making a proton. Here, Brownstein and Lowry says, okay, they lose a proton. Arrhenius says you produce a proton. Same thing, lose, produce. It's a proton. You're making it one way or the other. Where they differ is their definition of a base. Okay. And even though the hydroxide is not involved with this definition, the fact that the hydroxide can do what I explained earlier, how it has lone pair of electrons and the proton comes into play and creates a bond. Well, the same thing happens here. If you recall, when we did the Lewis dot structure for ammonia, here's ammonia. And this is true for any type of chemical compound that has lone pairs. They can act as a Brownstein-Lowry base, okay? Both cases, they produce a proton, either Arrhenius or Brownstein-Lowry. Where they differ is a base. Brownstein-Lowry classifies as a base as any chemical that accepts that proton that was generated. Now, how does it mean by accept? Okay, well, it has to do with lone pairs. If we look at ammonia and recall how we did the Lewis dot structure for ammonia, guess what? We ended up with a lone pair on the central atom. Okay. Now, the proton, as I explained earlier, when it dissociates, it does not have any electrons in the outermost shell. Okay, that orbital, that 1s orbital is empty. And so it will form a bond. That lone pair on nitrogen will come in and insert itself into that empty orbital of the proton and form a bond, resulting in accepting the proton to form the ammonium ion. Okay, the ammonium ion. Remember the ammonium ion? We did the research structures in that too. Okay, and this is true for even the hydroxide, because I explained earlier, if this was a hydroxide and it had, you know, two lone pairs here, well, that proton's going to do the same thing, form a bond. Okay, except in this case, with Arrhenius, with base, with hydroxide, it forms a neutral compound. With Brownstedt-Lowry, it actually forms a polyatomic ion, which is the ammonium chloride. Okay, the ammonium chloride. And so the difference between Brownstedt-Lowry and Arrhenius with respect to a base is that the Brownstedt-Lowry bases generally have nothing to do with hydroxide. It just happens to do with lone pair of electrons in which they can tie up and accept that proton. Okay, and that what that did was open up the definition of a base into a lot more chemicals that can act as a base and had nothing to do with hydroxide. Okay, so HCl loses the proton and the ammonium ties up the proton. All right, now the topic of strong acids and strong bases, which is related to what I explained earlier. The difference between the two is how much they dissociate in the solution. Okay, if they dissociate literally 100%, guess what? It's strong. If they don't, much less, guess what? They call it weak. Okay. All right. That's what we're going to talk about. But you know what? Tell you what, let's take a quick break. I got 2:20, 2:40. Let's call 15 minutes, come back in 2:55. 2:55. What do you think? All right, let's do that. And we shall return. All right, back. Looks like I'm losing a few people here. Okay. All right, well, let me go back to where I ended up. Okay, so in this scenario, in this part, I should say, we're talking about strong acids and strong bases. And as I stated, when we talk about strong acids and bases, we're talking about the extent of protons in either hydroxide. And most of the time, this point forward, when we talk about bases, we're mainly talking about anything that produces the hydroxide ion. Okay, so here's three strong acids. Okay, HCl, HNO3, which is nitric acid. Remember, it comes in NO3, comes from the nitrate ion. You put the hydrogen back on, okay, and you form nitric acid. You might wonder. Let's do this for example. You have HCl reacting with, say, sodium hydroxide. Well, you generate the sodium chloride plus water. Okay, so you got the chloride ion. Well, when you put the hydrogen back on, Okay, put the hydrogen at the proton back on, you form HCl, which is hydrochloric acid. Okay, the nitric acid reacts with sodium hydroxide to form water. Here's a hydroxide, one proton, one water, and guess what? The nitrate ion, in this case, sodium nitrate. Okay, if I take the nitrate, put the hydrogen back on, I get nitric acid. Guess where the SO4? Remember SO4, the sulfate polyatomic ion? Okay. So anyway, these three are strong acids, which basically says they deionize, they form ions, they dissociate 100% in a solution. Okay, now with respect to bases, potassium hydroxide, sodium hydroxide, they're considered very soluble in water. And because they're considered soluble in water, they will dissociate 100%. Now, note the difference here. Let me send you to the periodic table. Oh, wrong one. Sorry about that. Where'd it go? Oh. To the periodic table. If we look at the periodic table and we look at the bottom right corner, there's solubility rules. Okay. And look at this group. We're going to talk more about these here in a bit. But these cations, lithium, sodium, potassium, and ammonium, regardless of who they are bonded to, as far as the anion part, the negative part, okay, they're always considered as soluble. Always soluble. That's their classification. This whole column, the first column 1 through 5 is a soluble column. So lithium hydroxide, sodium hydroxide, potassium hydroxide, ammonium hydroxide are considered soluble. Considered soluble means that they will dissociate 100%. Hence, they will be considered as strong bases because you've got the hydroxide in there. Okay. Now the book just throws it at you and says, okay, these guys are strong. Well, then I'll explain to you why they're strong. Okay. All right. Again, the acids are soluble because their solubility in water 100%. Okay. All right. So this is what we consider strong acids and strong bases, which means if we had solutions of these acids and bases, and we had a little LED reader that you did in the lab yesterday, we immersed them in that solution, that little LED should just light up bright because the solution is basically all ions, okay? Now, one added thing, if I ever have to explain or write and describe from a schematic diagram, a beaker diagram, that this is strong, and so I would do it in this manner. This represents my beaker. Since this is a strong acid, that means that literally everything's 100%. So I would draw it with all, at least 3 pairs of anions and cations in there, something like that. Okay. And so everything's not combined, everything's all separated. Don't forget the charges. And the same is true for the strong base. Okay, this is a little beaker. And so I would have my hydroxide. Don't forget the charges on the hydroxide, my hydroxide ions, and then the counter sodium. Okay. So these would represent, these beaker diagrams, schematic diagrams on the right would represent a strong acid and a strong base because everything is dissociated, everything is separated. Okay, and here we go. That's the diagram. I would add, 3 to 5 sets of ions. Don't forget the charges. I mean, if you just throw hydrogen up there and the chloride and don't put the charges, that would be incorrect because these are ions. And we should know now, based on what you did in conductivity experiment, these ions will conduct electricity. And they conduct electricity because they have charges in them. So be able to pass that current, it closes a circuit. Okay, so those charges are important. And we draw them again totally dissociated because they're strong acids and they're strong bases. So those are the 3 strong acids: hydrochloric acid, nitric acid, sulfuric acid. The strong bases simply because of their solubility, because we could add lithium here and we could add ammonium hydroxide. Okay, those are also be strong acids and strong bases. In fact, the book should be lithium hydroxide and the ammonium hydroxide. All would be, 4 of them would be a strong base because they're all soluble. Okay? Again, what it means again is the fact that they're all soluble in solution and this literally dissociate 100% and then into their respective ions. The acids, remember, produce protons. Look at sulfuric acid. Okay. Well, let's compare hydrochloric acid versus sulfuric acid. If I were to ask you to draw the diagram, to draw the formula, the reaction, the process of hydrochloric acid dissociating versus sulfuric acid, how many protons would sulfuric acid have in solution compared to hydrochloric acid? Look at here. What's that number right there?
2.
2. So if sulfuric acid were to dissociate, and I were to draw an arrow like this, then I would produce 2 protons and the SO4 sulfate ion. Okay, compared to both nitric acid and hydrochloric acid, where they would only produce 1 proton plus the corresponding anion. In this case, 1 proton plus NO3, which is the nitrate ion. Okay, so sulfuric acid would produce 2 protons in here. And so when you recognize that, when we're gonna react sulfuric acid with the base, you got to remember that I got 2 protons. That means I'm going to need 2 hydroxides to neutralize those 2 protons, which will produce 2 waters. Okay, more on that here in a bit. Now, with respect to weak acids and weak bases. Now, the difference is that they do not dissociate 100%. In fact, they can vary from 1 to say 5%, and maybe even as low as 10%. It depends on the acid, but on average, we say 1 to 5%. That means that only 1 to 5% of the acid actually forms ions, and the other still remains intact. But to describe that, we use double arrows. Note the other examples we've been talking about. The arrow has been one direction. See, from left to right, one direction. But when we get something that's weak or a process that can go both ways, if you will, we use double arrows. Right here, which tells us that the rate of the reaction in the right direction equals the rate of the reaction in the left direction. A good example of this equilibrium, this is what we call an equilibrium reaction. If you take a soda pop, closed, and you shake it up, of course you can see the carbon dioxide coming out. Okay. Well, prior to that, there's nothing happening. Everything's in equilibrium. Okay. There's carbon dioxide in the space of your soda drink, in the airspace, and then some of it's going back into the aqueous and some of it's coming out of the aqueous solution, going back and forth until it finds a state of equilibrium. Okay. Now, the moment you shake that bottle, what happens? It starts to bubble up. So now the equilibrium has been shifted in one direction to the right to generate more carbon dioxide to get up in there, increase the pressure. Now, if you let that bottle sit, what happens? It goes back to its initial state. Okay, eventually it goes back to its state of equilibrium. And that's what we mean. That's what we mean by a double arrow. It's going back and forth from the liquid to the air, back and forth. So this is an example. Here's a formula for acetic acid. Okay, it's an organic acid, and it's written with hydrogen up front, so you can note that this is an acid, this is an organic acid. Okay, and it is a weak acid. So vinegar is a weak acid. And so when we place it in an aqueous solution, it will generate a proton, denoted by here, and the corresponding anion, which is the acetate polyatomic ion, which you find in the polyatomic ion table. Okay. All right. And that means that it has not totally 100% dissociated. Okay. So if I wanted to draw this in a diagram, beaker diagram, I would show at least one set of ions, like so, and then the rest, H2, H3O2, and I can just put like a 4 in front of it. I don't have to write all of them. And that shows that they're intact, okay? And they're in solution and just roaming around intact. But there's at least one set of ions in solution. It will conduct electricity, but it will conduct it very weakly because there's not a lot of ions in solution. So again, with our LED instrument, a little instrument will put in the probes in the solution, and the LED lamp would light up, but it would be a weak light up, not as strong as, say, the other acid, like hydrochloric acid and so forth. Okay. Now, these will react with the base because you're producing the proton. And when they react to the base, it will just cause the equilibrium to move to the right until all of the intact acetic acid or weak acid gets utilized and neutralized. So it will completely react with an acid. So try this at home. You can try vinegar and baking soda. Baking soda is a carbonate, which is a weak base. It will react, sodium bicarb, and you'll see that bubbling going on. Eventually, you will neutralize all of that vinegar. Okay, you neutralize because you notice no more bubbling action occurs as you add more sodium bicarb. All right. Now, with respect to a weak base, again, we are dealing with hydroxide. Now, the difference is this. Now, on the left, another example, let me show you here. The first, hold on. Where is it? There it is. Okay. Here's an example of weak acids. The first one is called hydrofluoric acid. Okay. If you ever do any, like a hobby of staining glass and things like that, you will have used hydrofluoric acid. It works well with staining glass. The next one's carbonic acid, H2CO3. CO3 is the carbonate ion. Put the hydrogens back on. Remember, carbonate CO3 -2, put the hydrogens back on. You have carbonic acids, find that a lot in soda pop. The next one is vinegar, aka acetic acid, and then H3PO4, which is called phosphoric acid. Now those are weak acids and therefore do not dissociate 100%. They will dissociate much less, 1 to 5%. Okay, and as far as conductivity, they would exhibit low conductivity of electricity. All right, now with respect to weak bases, and we're still talking about the hydroxide, another a way to designate before I proceed with that is I did use acetic acid as an example on how to show how it's weak in the diagram, but this one here, they use HF, hydrofluoric acid. Notice they use one set of ions. You got to have that one set of ions, and then put in about 4 or 5 sets of combined acids. So notice the HF is intact. They're not separated into ions or together, and they're just floating around in solution. So, and the 2 ions just show you that it's a weak acid. Much different than hydrofluoric acid, where all of the ions are separated. Okay. All right. Which brings us to weak bases. One weak base is called magnesium hydroxide. Okay. Now they just throw it out there again and say it's a weak base. Well, there's more to it than that. It's a weak base because it is classified as insoluble in an aqueous solution. Okay. The fact that it's weak means that because it's an ionic compound, here's the thing to remember. It's an ionic compound. So when we want to depict, and it's weak because it's classified as insoluble, and we want to depict it on a diagram, we will show the bulk of it down at the bottom of the beaker. Unlike an acid, which is a liquid and will just float around in the solution. It will not fall down to the bottom like a precipitate does. This is magnesium hydroxide, and this little chunk is down in the bottom of the beaker to describe that the bulk of it falls to the bottom. Good example of this is milk of magnesia. If you take milk of magnesia in a clear container and you let it sit, you'll see that a lot of that solid goes down to the bottom of the container. It eventually settles down there. That is just material that is insoluble. Okay. Now, the fact that it's weak doesn't mean it doesn't dissolve, because what we do is we show at least one set of ions in solution. And we show 2 hydroxides, obviously, because magnesium is a +2. Hydroxide is a -1, so there's 2 hydroxides. So when it dissociates, we're going to produce 2 hydroxides. Okay. So the diagram on the right shows, it depicts a weak base. Now, how do we know it's weak? Because of its solubility. So let's go back to the solubility rules. We're going to talk at length about these. Okay. But here we have the hydroxide, which is number 10. Normally, hydroxide is in the insoluble column on the far right, meaning that whatever hydroxide is bonded to, it is insoluble, unless it's bonded to a certain element, and I'll come back to it. Right now, we did a magnesium hydroxide, okay? And magnesium hydroxide, magnesium is not one of the ones that it bonds to make it soluble. So magnesium hydroxide is just classified as insoluble. There are exceptions, specifically 4, 5, 6, 7 hydroxides that are soluble, and I'll just go ahead and just explain which ones they are. If the hydroxide is bonded to calcium, barium, or strontium, or is bonded to any of the I call them the Fantastic Four. If it's like lithium hydroxide, sodium hydroxide, potassium hydroxide, ammonium hydroxide, calcium hydroxide, barium hydroxide, strontium hydroxide. There's 7 hydroxides that are classified as soluble. Otherwise, anything else that is bonded to is insoluble. Magnesium is not part of the 7, okay? So that means that magnesium hydroxide is classified as insoluble. Classified as insoluble doesn't mean that it's insoluble 100%. It just means that maybe 1 to 5% of it goes in solution and the rest remains intact as a precipitate and falls down to the bottom of the container. Okay, and we designate that down at the bottom container because it's an ionic compound. If it was a covalent compound, like HF, then it would be floating around in the container. Okay, so it's a weak base. In both of these cases, would exhibit conductivity lightly, weakly. The LED would be a weak color, okay? Because not so many ions in solution. All right, so these are the weak acids: hydrofluoric, carbonic, phosphoric, and acetic acid. Okay? And the weak bases are, in this case, is magnesium hydroxide, but it can be any hydroxide other than those 7 we just mentioned based on the solubility. So it could be any hydroxide, and it makes it a weak base because any hydroxide other than those 7 makes it classified as insoluble. And I can't overemphasize when we say insoluble, does not mean 100% insoluble. It just means that a little bit will go in solution and the rest would remain intact. Okay. And that's what we're talking about. I mean, so if we look at the general diagrams, okay, and the question says, which one is a strong acid, A, B, C, or D? What do you guys think? Which one would depict a strong acid? Here we got A. That is correct, Rachel. Because when we compare A, all of the ions are separated. There are no ions that are intact. So they just literally nearly 100% ions. When we compare it to B, yeah, there's some ions in there, but there's some HA that are still intact, and the same with C. And with respect to D, there are no protons in there at all. Okay, so A would be the strong acid. What about the weak acid? Which would depict a weak acid? Since A is a strong one, we've got a choice of B, C, or D. What do you think? B, C, or D is the weak. Okay, C would be a weak acid, but wouldn't B also be a weak acid? B and C would depict both, 2 weak acids. But let's take it one step further. When we look in B and C, we're both weak acids because the bulk of their material is still intact, the HA. But could I say which one is a stronger acid, B or C? They're both weak, but of the weak acids, which one could I predict to be a stronger acid?
Maybe C?
Which one?
C?
B? Yeah, why would B? Okay, well, we got C here. Rachel says C. We're dissociated. Count the number.
I said C.
Okay, C. And why wouldn't B be the stronger acid between B and C?
It looks like they're more expanded.
Oh, okay, Rachel, there you go. Yeah, B would be when comparing. Now we agree that B and C are weak acid when compared to A. A is a strong acid, everything's associated. B and C are weak acids because they're not totally 100% dissociated. But within B and C, we could even take it one step further and say that B is a little bit stronger than C simply because C has more protons in solution, okay? Depicted by the picture. B has what, 2 protons and C has 1 proton, okay? So if I had to make a guess, and I'd say, yeah, B is a little bit stronger than C. And they're both weak, but B is a little bit stronger because it has more ions in solution. And then as far as it being a base, we really don't have a base here because there's no hydroxide being generated. And when we talk about bases, we're going to stick with the definition of OH. But be aware that the Brown-Sedlari has nothing to do with the hydroxide ion, but has to do with any species that will accept the proton. All right, which brings us to the pH scale. Okay, the pH scale, you may be familiar with this. In fact, if you have, let's say, a swimming pool at home, I'm sure you got to check the pH, make sure the pH is okay. If you have, let's say, an aquarium, I'm sure you're checking the pH. So what it is, pH is nothing more than a number. Okay, the scale starts out with 0 on the far left and goes all the way to 14 on the far right. Neutral pH is a 7. Okay, a 7. So anything less than a 7 pH is classified as acidic, and anything greater than 7 is classified as basic. Another name would be alkaline. It's either acidic or alkaline, and 7 is neutral. Okay. Now we're introducing a new concentration unit here. You got to see we're talking about protons and hydroxide ions in their concentration, and that's what the brackets around here, for example, the bracket around the proton and then the bracket around the hydroxide. What it's saying here, when the concentration of the proton is greater than the concentration of the hydroxide, we have acidic solution, okay? When the concentration of both the proton and the hydroxide ion are equal, then we have a neutral solution. And then when the concentration of the hydroxide ion increases and becomes greater than the proton, then it becomes alkaline in nature. Okay? And there's a variety of things here we're going to talk about as far to give you an idea where the acidity is. And something to think about here too. I mean, now that you're learning chemistry, you're learning about an acid-base reaction. You've learned hopefully that in your stomach you have hydrochloric acid, which is obviously an acid. And then whatever base you take, you ingest, that base gets neutralized, like the Tums. Okay. And so now think about this. If you buy and drink alkaline water is a basic water. And when you ingest it, what is going to happen to that water you just ingested while it's in your stomach? And believe me, the acid-base reaction is spontaneous. It's not something that takes a little time. It's spontaneous, it reacts quickly. So you all seen that water is called alkaline water, seen it advertised. Now, as you ingest it, what do you anticipate is going to happen to the alkaline water once it passes to your esophagus and enters your stomach? Any ideas? We all agree that if you take Tums, you're going to neutralize the acid. Tums is a base, alkaline, stomach's the acid. So we all recognize that, right? You take that or milk of magnesia or something that's a base, and you ingest it, So now if you drink alkaline water, what is going to happen to that water when you ingest it? Wouldn't the same thing happen? Yeah, because that water is alkaline. There's a lot of water out there that has a pH greater than 7, so it's classified as alkaline water, 9 to 10. Okay. And then when you ingest it, it's going to react with the acid in your stomach and get neutralized. So whatever benefits you have with respect to alkaline water, I don't know, other than which remains is a bunch of salts. All right. Now, the water around, what I used to do when I taught in Kansas City, I used to have students bring in samples of water in wherever they lived. And my students were dispersed through all the Kansas City metro area, and they brought in water. And I was really surprised. We were all surprised. The diversity of pH from as low as around 3, which is very acidic, to as high as about 11. And then to make even matters more interesting was, I know everybody likes bottled water and you drink it quite a bit, but I also did a research of studying bottled water and looking at the number of ions, sodium content, looking for organic residue, organic material. And I haven't checked it lately, but in this time period, a lot of it was not the best. So, people were drinking soda water and you had to minimize your salt content, and drinking that tap water and that bottled water wouldn't be good because the salt content was pretty high, the sodium content. So health-wise, it wasn't great. A lot of them were contaminated with organic compounds. Big mess. pH varied quite a bit. Very interesting. Anyway, food for thought. Trying to get this knowledge of chemistry you have and trying to bring it into the real world. All right, let's clear this up. So that is the pH scale. Now, that bracket around there, like I stated, deals with the new a concentration unit, specifically molarity. And we're going to have more about this down the road here, but moles is a unit that we're going to learn quite a bit about. Moles is very important in chemistry. First time I saw it, I thought, mole, what are we studying mole? No, it's moles. And it's nothing more than a number. I may have mentioned already what that number is, but it's a ratio of moles over volume, okay? So that's all we're talking about, the bracket. Now, we talked at length about the acidity and the basic nature of the water, all depending on the concentration of the proton. If it's greater than hydroxide concentration, then it's acidic. If it's less than hydroxide concentration, then it's basic. If they're both the same, then we got a pH of 7 or neutral. Okay. Now, how do we calculate the pH? Now, pH is nothing more but a numerical value. Specifically on your calculator, you have a button called the log. Okay, you don't have to do this longhand. When you got a calculator, scientific calculator, all you need to do is just push the log. Because specifically, it is the negative log of the proton concentration. So what you do is you type in the proton concentration, then you hit the negative log, you hit the log, and what happens, you get a negative number. And when you multiply that with a negative, you get a positive number. So the pH always ends up being a positive number, okay? If you want to invert it, go back to the concentration, you have a button in your calculator that's labeled 10 to the X power. So what you do is you hit that button 10 to the X power, then you type in the negative pH, and then it sends you back to the concentration, okay? So for example, if we have a concentration of 1 times 10 to the negative 1 moles, we plug it in the calculator, hit the log, we end up with negative 1 times negative 1 is a 1, positive 1. Okay, So a concentration of a 0.1 solution is 1. So it's very, very acidic. Okay. 1 times 10 to the negative 5th has a pH of a 5. You might see a trend here when you're using scientific notation. Okay, 10 to the negative 8 has a pH of 8. Now, pH of 5, it's still acidic, not weakly acidic, but it's getting close to 7. But when we hit pH of 7, it's over pH of 8 is over 7. 7 is neutral. So now we're getting into the alkaline range. 10 to the negative 3, 1 times 10 to the negative 3 gives me a pH of 3. We're back to the acidic range. Okay, now I can either type it in scientific notation or I can just put it back in long form. So 0.001 is the same thing as 10 to the negative 3, okay, which is the same pH. And then take this one here, type it in, you should have a pH of 8. So either written as 0.0000 or 10 to the negative 8, same scenario. Right, so that's how we calculate, if we need to calculate the pH. And if we have a nice even number, 1 times 10, whatever, we just know that the exponent is the pH. Otherwise, you have to type in the whole thing in the calculator if you need to calculate an exact pH. Okay. Some example of pHs, vomit, you might say, well, it gives you an idea as to the pH of your stomach because it's going to vary. It's going to vary from individual to individual, but it's going to be acidic. Okay, lemon juice around 2, coffee. Again, it really depends on the brand, but most coffees are around 5, meaning it is acidic. Okay, saliva again varies from person to person, but most of the time it's neutral. Blood, very crucial pH, very important pH. You have to maintain that pH around 7.3 to 7.4. Slight variance from person to person. Here's milk or magnesia. That's something when you take that you have a upset stomach, too much acid reflux. It's a base. Okay, you ingest it, it will react with the acid in your stomach and reduce the acid content. Okay, ammonia has a pH pretty high, almost 12. Urine, it varies from individual, but on average, it's acidic. Okay, soda pops, most colas anywhere from 2.5 to 3.5. And root beer, for some reason, is a little bit more, not as acidic as the others, but a little bit closer to neutral. Okay, now with respect to what we got here, what we call buffers. All buffers do is maintain a constant pH. So we can make a buffer of the whole pH scale. If, for example, a classic example is your blood. There is a buffer system in your blood system that helps maintain that pH of 4. Involved a lot with the carbon dioxide intake, involved with the bicarb that's in your solution. And it's very crucial that you maintain that 7.4-ish pH, okay? So your body's working hard. And it does that using what we call a buffer. And what that does is you have components of an acid in the base in this buffer. And so if an external acid comes into your system, the base of your buffer will react with that acid and neutralize it and try to maintain the pH. And vice versa, if a base comes in, the acid of that buffer system will react to help maintain that pH, okay? And we use it quite a bit in chemistry. Sometimes we get a runner reaction at a very specific pH. And so we make buffer solutions for that pH and then run a reaction at that pH, okay? All right. Now, looking at this reaction, what we have here is nitric acid, HNO3. We got to start recognizing we're looking at reactions now, okay? We started with the elements, okay? From the elements, we started putting down ionic compounds. We started introducing acids, ionic compounds and covalent compounds, and now we're going to have these things react with each other. Okay, so we have HNO3, which is an acid, okay, specifically nitric acid, and then reacting with, which is the plus symbol, calcium hydroxide. Well, calcium hydroxide, we know from what's in the parentheses that we have an acid reacting with a base. Okay, and we recognize it as an acid because hopefully you can see we got hydrogen written first, so we got an acid. Okay, second of all, we recognize as a base because we got the OH in parentheses, and even more specifically, there's two of them. And so what happens is when we put this in solution, we're going to get calcium ion plus 2 hydroxides. Okay, and we put the nitric acid in solution, we're going to get the proton plus the nitrate ion. Okay, now that's the reactants. Now, how do we get to HNO3? Well, we have to recognize, remember earlier I said to you, follow the protons and the hydroxides. We have 2 hydroxides here that are generated from the calcium hydroxide. If we need to neutralize those 2 hydroxides, we're going to need 2 protons. So we're going to need 2 nitric acids. And hence we put a 2 in front of HNO3 to tell us we have 2 nitric acids. With that, now we get the 2 protons reacting with the 2 hydroxides, and guess what we make? 2 waters. Okay, 2 waters. And now you notice that the corresponding salt, what is left, they just fall into play. We know calcium is a +2, the nitrates are a -1, and it generates this formula, calcium nitrate. And we have balanced this equation, okay? You might say, well, let's double check. Is it really balanced? Well, yeah. Okay, total, we have 2 hydrogens coming from the nitric acid, 2 hydrogens coming from the hydroxide. So we have 4 hydrogens on the left-hand side. We have 4 hydrogens on the right-hand side coming from water, okay? Now, we got 2 nitrate groups. So 2 nitrate groups. My recommendation is not breaking up nitrogen and oxygen, just recognize you got a nitrate group. So I got 2 of them, and I got 2 of them on the right-hand side. So my nitrate groups are balanced. I got 1 calcium, and lo and behold, 1 calcium. Okay, now I go back, everything's balanced. I have a balanced chemical reaction. Okay, Mother Nature's happy. Now, another takeaway, once you got it balanced, now you can look at this reaction and say that I need 2 molecules of nitric acid, 1 molecule of calcium hydroxide, will use 2 molecules of water and 1 molecule of calcium nitrate. So let me put them all together like this. I got 2 nitric acids, 1 calcium hydroxide, 2 waters are created, and 1 calcium nitrate. Okay, that's our breakthrough. So you can see that. And since instead of having to write all this out, that's why we use the coefficients to put it in front. We are balanced. The relationship between nitric acid and calcium is a 2-to-1 ratio. Okay, 2-to-1 ratio. Think about this for a second because you're going to use this down the road. If, given what I just told you, that the ratio between the nitric acid and the calcium hydroxide is 2:1. If I start off with 4 calcium hydroxides, how many nitric acids am I going to need? Good. You can do it. If I have 4 calcium hydroxides, how many nitric acids am I going to need for this reaction to start out? This is a concept that we really have to grasp. Okay, what do we got here? We need 2, not quite. Think about this for a moment. If normally I need 2 nitric acids for 1 calcium hydroxide. If I have 4 calcium hydroxides, how many nitric acids do I need? 8, you got it. I'm going to need 8. 8 of them, because my ratio is a 2:1, okay? So, and that relationship that I just did, that I was just trying to demonstrate, will be important when we say, okay, if I start off with 10 grams of calcium hydroxide, how many grams of nitric acid do I need? And I'm going to need that balanced chemical equation with that ratio of 2:1 to be able to answer that question. Right now, we just talked about how many molecules. But in reality, we don't go to the lab and count the molecules. We go to the lab and count grams. So we got to take one more step and convert that grams into that number, that factor we introduced earlier called moles. Much more in that. But right now, you're getting the beginnings of the type of reactions that we're going to be working with. Good. There was something else I had to say about this. Yeah. So anyway, who is the Arrhenius acid here? HNO3 or CaOH2?
HNO,
Which one?
HNO.
HNO3. Nitric acid is the Arrhenius acid. Obviously, the hydroxide, the calcium hydroxide, is the base. And of course, calcium hydroxide has 2 nitrates because calcium is a +2. Okay, +2 ion. Came from group 2A, so it will have a +2 ion. All right, in this scenario, what they want you to do is to draw pictures of nitric acid, hydrofluoric acid, potassium hydroxide, and magnesium hydroxide. Well, before we can draw pictures, we have to define it as it being strong or weak, whatever it is, okay? Well, HNO3 is one of the strong acids that we talked about earlier, okay? So this is strong acid. HF was one of the weak acids we talked about earlier. Potassium hydroxide, well, recognize again hydroxide, so it is a base because of the hydroxide. And then based on the solubility rules, which we're going to learn about, potassium was one of those 4 that no matter what is bonded to potassium, okay, it is soluble. And if it's soluble, then this makes it a strong base. And another base is the magnesium hydroxide, which is a base, okay? But based on the solubility rules, when it is bonded to magnesium, it is classified as insoluble, which makes it a weak base. And the thing to remember about, even though it's classified as insoluble, does not mean that it will not dissolve 100%. It just means that 1 to 5% of it will be dissolved. The rest of it remains intact. Okay. So to be able to draw pictures of whatever you need to draw, you have to first classify it as strong or weak, whether it's an acid or a base. Okay. All right. So all right. So as we stated, HNO3 is considered a strong acid. So we got 100% dissociation. Okay. All the ions are separated. There's nothing intact. HF, again, it's an acid. Okay. And it's on the list of being classified as a weak acid, which means that we have some ions, okay, but the bulk of the material is intact. So when you have a weak acid, I would just show one set of ions, okay? And then, have at least 4 or 5 sets of intact formula, HF intact. Okay, so this depicts a weak acid, not a lot of ions in solution. It will conduct electricity very weakly as compared to nitric acid, where it will conduct electricity strongly. Potassium hydroxide, because of the solubility, is classified as a strong base. I'm trying to get this thing because why? In the solubility rules, number 1, these cations, lithium, sodium, potassium, ammonium, these are cations. Whatever they are bonded to, whatever anion they're bonded to, doesn't make any difference. There's 10 billion of them out there. It is soluble in water. And the fact that it's classified as soluble means that they will dissociate completely. So potassium hydroxide, 1, is a base, and 2, it is a strong base because it is soluble. And we will depict it with all the ions totally separate. Okay? Now, with respect to the last one, again, it is a base. The question is it a strong base or a weak base? Well, to answer that, the fact we're dealing in both cases for potassium and magnesium, the fact we're dealing with ionic compounds, they're not covalent, they're ionic compounds. We go through the solubility to determine what they are. Okay. If we look down at the hydroxide area, normally hydroxides, no matter what hydroxide is bonded to, is insoluble, okay? Unless they're bonded to the 4 and then plus the 3 more that they put in here, calcium, strontium, and barium. Magnesium is not one of those 7. Therefore, it is classified as insoluble. And being insoluble, again, does not mean that it is like 100% insoluble. It means that the bulk of the material is down at the bottom of the container because it's settled down over time. Okay, but we have to show at least 1 set of ions in solution. And we show 2 hydroxides because it's magnesium hydroxide in parentheses, meaning there's 2 OHs for every 1 magnesium ion. So when they dissociate, we're going to produce 2 OHs. Okay? So that depicts a weak base. So we have an example of a strong acid, weak acid, strong base, weak base. Note the difference in how we depict the ionic base. The precipitate, it settles to the bottom of the container. With respect to a covalent weak acid, HF, it's still in solution. It's not a solid, it just goes straight down. It just is dissolved in solution, dispersed throughout the solution. Okay. All right, let's summarize this. We have the Arrhenius acid, by definition, produce or make proton ions in water. The base, Arrhenius base, makes the hydroxide ions in water. Okay. The Brownstedt-Lowry acid loses a proton. Think about it. Whether you lose it or you produce it, or you make an ion like the Arrhenius, you're producing. There's a proton. So the definitions are essentially the same. Okay. Either way, there's a proton involved. Where they differ is the base. Okay. Where the Brownstedt-Lowry, what it does, it accepts that proton. So does a hydroxide, but what Brownstedt-Lowry did is allowed more compounds to be defined as bases that had nothing to do with the hydroxide. Okay? All right. When we talk about strong acids, we're talking about acids that when they ionize, okay, when they dissociate to form ions in solution, essentially they're at 100%. The same for weak ones, they're going to ionize much, much less, 1 to 5%. Okay, so in both cases, they're going to conduct electricity. The difference is the strong acids will conduct more electricity than the weak acid, simply because the amount of ions in solution. And it's the ions that carry the current through the solution. Close that current, close that circuit, if you will. Strong base, like these strong acids, will dissociate 100%. When we talk about bases, we are talking about ionic compounds that deal with hydroxide ion. And then furthermore, we're talking about their solubility in an aqueous system. When we dealt with strong acids and weak acids, they are covalent compounds, okay? And we're telling you, and again, they deal with solubility, and we don't have a table to describe that. We're just telling you this is a strong acid, and it's a strong acid because it's soluble in aqueous systems compared to acetic acid, which is a weak acid because that is soluble. Well, solubility also plays a factor, but we do have a table that we can predict solubility. And based on the hydroxide, we can determine whether a hydroxide is a strong based on the solubility table. And if it's classified as soluble, then it is a strong base and it dissociates 100%. If it's classified as insoluble, just means that there's going to be a small amount of ions in solution. The bulk of the base remains intact and precipitates down to the bottom of the container. Okay. And what buffers do, basically all they do is just maintain the pH, whatever pH value you need to maintain. Some more examples of different soda pops. I was really, tap water can vary depending on where you're at and who's cleaning up your water. But you can see root beer is pretty high. And then RC Cola, that used to be my favorite way back in the day, very acidic. Okay. Why is this important? Because dental hygiene, basically, you can cause enamel erosion if pH is below 5, and long term can cause problems like salt. Okay. Anyway, this brings us to the solubility, so we didn't get a chance to really talk to them in earnest, but that's what we're going to do now, and then that's going to end this chapter. We'll probably call it a day. Okay. When it comes to solubility, we have to be specific. And we have to talk about temperature, because temperature is a factor. We all know, or maybe we don't, but if you're trying to cook something and we want to dissolve it, we first dissolve it at room temperature and it doesn't dissolve. What do we do to get it into solution? Any ideas? What can we do to get some material? Maybe we're cooking something and it's not going in solution, we're making a solution to something. What can we do to get it in solution? Any ideas? Yeah, we mix it, yeah, but even at mixing, it may not work. So what else could we do? Mixing will work, of course, yeah. Ah, there you go. We add heat, okay? So heat is a factor in solubility. So we have to be careful and be very specific when we talk about solubility. And so, excuse me, the solubility rules, excuse me, the solubility rules are based on 25 degrees Celsius, okay? Second of all, they deal with ionic compounds. And so we're going to be dealing with simply strict, just ionic compounds. When something is classified as being soluble, what it says that the compound in aqueous solution essentially dissolves completely. And we use the physical state of, in parentheses, AQ, okay, saying that it is soluble and it's an aqueous system. If it is classified as insoluble, we use the physical state of S to designate it as soluble. All right. Now, remember this. When we talk about conductivity of ionic compounds, if it is soluble, that means it'd be a very strong conductor, strong, what we call electrolyte. You know, you're all familiar with the term electrolyte. You probably buy drinks because you want electrolytes. Electrolytes are nothing more than the atoms that have lost or gained electrons. So sodium, the chlorate, phosphates, sulfates, whatever you're ingesting, those are electrolytes. Okay, and these are anions or cations. All right, so something that's classified as soluble means it would be a good, strong conductor of electricity. So it would make it a strong, whatever it may be, strong electrolyte, strong base, strong acid, okay? If it's classified as insoluble, then not so much of it's in solution. The majority of it is intact. Now, these solubility rules are important because there's another type of reaction that we're going to talk about. We just talked about your first reaction, acid-base reaction, but there's another type of reaction called double replacement reaction. We're going to get a lot more on this in the next chapter. And that reaction is dependent on the solubility rules as far as the new products. If you mix A and B together and you create new products, and one of them is classified as insoluble, then we get a positive reaction. If the products are classified as soluble, no reaction. So these solubility rules will help us predict those type of reactions, okay? Now, how does this work? Okay, well, we got the table here, and on the left side is the soluble side, okay? And as I mentioned earlier, that the big four here, lithium, sodium, potassium, ammonium, that those cations, that whatever they're bonded to make a difference what it is, they will always be classified as soluble, okay? And that's the cations. Now, we have the acetate ion. That came from acetic acid. When acetic acid reacts with the base, the salt that is generated is the acetate ion. When that anion is bonded to whatever cation you may have, to make a difference what it is, copper acetate, gold acetate, of course, lithium, sodium, potassium, and ammonium, that's always the case. But whatever metal is bonded to acetate, it is soluble, okay? The same is true with nitrates. whatever metal or cation is bonded to the nitrate, it is soluble. Okay, so again, here, I was having a mental block there. Iron nitrate, cobalt nitrate, copper nitrate, zinc nitrate, barium nitrate, strontium nitrate, calcium nitrate, etc. All soluble. Okay. Now here's the thing you got to a little bit twist. When it comes to the halides, remember the halides, chloride, bromide, and iodide. Normally, they are classified as soluble, except when they are bonded to silver, mercury, or lead. Okay, so when they are bonded to those heavy metals, we call them heavy metals, silver, mercury, lead, then they are insoluble. And we use that property to help us out, because if you have a water you want to look for like chlorides, you treat it with a little silver nitrate. We know silver nitrate is insoluble. If you have any chlorides, it will precipitate, because the silver chloride or silver bromide or silver iodide is insoluble, and it will precipitate. So that's a good indication that you have halides in your water, strong halides. Okay, all right. Sulfate ions, very similar to the halides in that they're normally soluble, okay, unless they're bonded to calcium, strontium, barium, silver, and lead. 1, 2, 3, 4, 5. Only 5 sulfate compounds that are classified as insoluble. All of the other ones are soluble. Okay, and again, calcium sulfate, strontium sulfate, they were precipitated when found in aqueous solution. And so if I have like potassium sulfate and I put it in another solution that has calcium, it will precipitate because it's classified as insoluble. Okay, so that's the left side of the column. Lithium, sodium, potassium, ammonium, always soluble regardless of what the anion is. The anion, acetate, nitrate 2 and 3, always soluble regardless of what the cation is. The halides, chloride, bromide, and iodide, normally soluble, except when they're bonded to the heavy metals, silver, mercury, and lead. Call them the heavy metals, but they are the big metals and cause a lot of headaches as far as health issues. All right, and then the sulfates normally soluble except for 5 of them: calcium sulfate, strontium sulfate, barium sulfate, silver sulfate, and lead sulfate. Those are classified as insoluble. Okay, now let's go over to, change the color a little bit, to the right column. And this is the insoluble column. Okay, so normally, and we're right at this point in time, we are dealing with the anion. The only cation we've been dealing with is on the soluble side, the lithium, sodium, potassium, and ammonium. Okay, but so by and large, we're just dealing with the anion. All right, so the carbonate, the chromate, and the phosphate ion. Normally, regardless of what they're bonded to with cation, is considered to be insoluble unless they are bonded to those 4. So there's only 4 examples of the carbonate that are soluble: lithium carbonate, sodium carbonate, potassium carbonate, ammonium carbonate. Everybody else, regardless of what it is, insoluble. Okay. The chromate is the same way. Normally insoluble unless it's bonded to the big 4. And the phosphate, very similar. Okay. So in the cases of chromate, carbonate, chromate, and phosphate, there's only 4 examples of each that are classified as soluble. The rest, regardless of what it's bonded to, is insoluble. Keep in mind what we mean by insoluble. If they were in a beaker, test tube, whatever, the bulk of it will precipitate, but there's still at least a little bit of ions in solution. Okay. All right. Now the sulfates similar in that they are normally insoluble regardless of who they're bonded to, unless it's the big 4. But on top of that, we got 3 more. So there's only 3 examples of sulfides that are soluble. And, besides the lithium, sodium, potassium, ammonium, you also have calcium, strontium, and barium sulfide, which are classified as soluble, but everybody else is insoluble. Okay. And the hydroxide is very similar. Hydroxide normally insoluble unless they're with the big 4, and then on top of that 3 more. So there's 7 examples of soluble hydroxides, and all the other hydroxides combinations are classified as insoluble. Okay, so that in a nutshell is basically how that table works. So any questions about that? And let's do some examples. All right, let's look at the first one. We have, what's the name of the first one? Na2S. Na2S. What would be the name?
Disodium. What was the last part?
Na. Yeah, this one here, the very first example. What would be the name?
Oh.
This one right here.
Oh.
Sodium part's correct.
Sodium sulfate?
That's sulfate.
Sulfite.
There you got it, sulfide.
There's no oxygen.
Yes, you got it. So it's sulfide. What about the name of this guy? This one here, guys.
Aluminum hydroxide?
You got it. How about this one? AG, remember what AG is?
Let's see.
I'll give you a hint. Jewelry. Don't say gold. Silver. Okay, so the second one is silver bromide. Okay. How about this one here? Trying to get the name. Ca would be what?
Calcium.
Calcium.
Chloride?
Chloride? No.
Chlorate.
No.
Hmm.
Okay, because what comes up next? You got carbon. Okay, right after the calcium, you got carbon, and then followed by oxygen. Okay, so you got carbon, oxygen, specifically 3 of them. So I'm hoping that would direct you to the polyatomic ion table.
Calcium carbonate.
You got it. And then finally, who's got this one? Anyone else? We'll let anyone else besides Teresa got this one? Okay, Teresa, go for it. Oh, there is somebody in the chat. Potassium nitrate. There you go, Rachel. You got it. All right, good. So we got the names. I'm trying to, be able to, you could be given the names of a formula and then be asked to write the names, okay, and vice versa in the nomenclature part. All right, so first things first. Now being asked, is it soluble or insoluble? Okay, and so what we do is we use the solubility rules. And so we see that the first one is sodium sulfide. Now, here's the deal. The first time, anything with these four, lithium, sodium, potassium, and ammonium, always 100% of the time, always soluble. So sodium sulfide, automatically, the fact that you see sodium right up front makes it soluble. And guess what? Potassium nitrate also makes it soluble. Okay, so we would write that with the AQ. Okay, all right, aluminum hydroxide. Well, we have to, come on, a mouse. Okay, we have aluminum hydroxide. Well, send us to the hydroxide section. Hydroxide normally, it is, not normally, it is in the insoluble column, okay? And normally whatever's bonded to the hydroxide is insoluble unless it's the four or calcium, barium, and strontium, of which aluminum is not. So therefore, what do you think? Soluble or insoluble?
Insoluble.
Insoluble, exactly. All right. Now, let's look at silver bromide. Okay. It's a halogen, the bromide. Okay. So we go to number 4. Normally, number 4 is in the soluble column. Okay. But there are 3 examples of halogens that are insoluble, of which that example makes it insoluble. And so silver bromide is insoluble, so we write the letter S. Okay. All right, now we go calcium carbonate. All right. Well, normally the carbonate's right here. They're insoluble unless the big 4, of which calcium is not of the big 4. So it is insoluble. You might be familiar with this. May have seen it someplace. A lot of times that ring around the tub, that is calcium carbonate. You have a lot of calcium in your water. There's definitely a lot of carbonate in our water. So, and it forms a ring. And sometimes there's that crust around your outlets and so forth. Again, it's calcium carbonate. It's not very soluble at all, and therefore forms a precipitate. So calcium carbonate is insoluble. And then finally, the last one, potassium nitrate. What do you guys think? Soluble or insoluble?
Soluble.
Definitely soluble because it's part of the big four there, potassium. Okay, so we have a soluble solution. Okay, now learning to use this table is important because when we talk about that reaction, what we do is we have two ingredients, 2 reactants, and I'm going to put it in general terms. Okay, you have A plus B, and then you're asked the question, okay, the new products you're going to make is C plus D. And whether the question is, would this reaction occur? Well, to answer that, we use the solubility rules here. And we look up C, and depending on the rules, determine whether it's soluble or insoluble. So for argument's sake, we see that C is soluble, say Q. But then D, based on the solubility rules, is insoluble. So we got solid. That means we got a positive reaction. If both of the new products were soluble, then it would be a negative reaction. Okay. So we'll be coming up to this type of figuring out here in the next chapter or so. And the solubility rule helps us to predict whether we're going to have a reaction or not. All right, let me kind of hurry here. Maybe not. Okay, with respect to electrolytes, strong electrolytes are good conductors of electricity. That's because they completely ionize the solution. And so anything that soluble ionic compounds, because of the solubility rules, strong acids, strong bases, things like potassium bromide, nitric acid, etc., would make strong electrolytes. Electrolytes are nothing more than these ionic compounds and covalent compounds and acids that have completely dissociated in solution. Okay. Non-electrolytes, we learned about that in class, or conductors, are things like covalent compounds, like the sugar compound. Sugar is a covalent compound. Other than acids, are these water doesn't dissociate, carbon monoxide, C6H12, that's a general formula for sucrose, the sugar. Non-electrolytes, because they don't carry a charge. Okay, they will not conduct electricity. And then weak acids, weak bases, any ionic compound that's classified as insoluble. Okay, and some examples are HF, magnesium hydroxide, silver chloride, and carbonic acid. Those would be weak electrolytes. Weak electrolytes. Okay. And so here's some a summary. Then strong electrolytes, we have strong acid, strong base, etc. Okay. And basically, this is what we did with our sensor, conductivity sensor here. You can see the red and the blue represent ions. And as long as they got a charge, then we're going to complete the circuit, and we're going to get electricity passing through. Okay. If the material in the solution are non-electrolytes, no ions, then no circuitry. So don't try this at home. But if you were to fill up your bathtub full of DI water, remember deionized water, that's water with no ions, and then don't try this at home, and I'm just using this as an extreme example, put your plugged in hair dryer in the water, it will not conduct electricity. And so there's nothing going on as far as electrical shock. In fact, you can stick your hand in there, nothing happens. Now, once you have your hand in there in a few minutes, I would definitely get your hand out, because now on the outside of your hand, we precipitate all day, and we got ions and so forth that we lose. That gets in the solutions, and now we got ions, and now you're going to have current passing. So I would unplug it real quick. All right. Okay, image, which is a strong, weak, or non. Basically, you can see in the far left, it is a weak electrolyte because it's insoluble. The bulk of the magnesium hydroxide is down at the bottom. It has a few ions in solution. The CH4 is a non-electrolyte. It's in a covalent compound, and so no electricity is going to happen. And then potassium chloride, we know based on the solubility rules that potassium bonded to anything is soluble. So that means 100% soluble here. Okay. All right. And BAS, barium sulfide, is a strong electrolyte because it's soluble based on the solubility rules. Silver chloride is a weak electrolyte based on the solubility rule because it's insoluble. Potassium nitrate, we had that earlier, strong electrolyte because it's soluble. H2CO3, carbonic acid, is one of the weak acids, and therefore it's a weak electrolyte. Carbon dioxide is a non excuse me, non-electrolyte because it's a covalent compound. It does not have charges. Number 6, sodium hydroxide, strong electrolyte because it's soluble. Okay, strong base. It's a strong base because it's classified as being soluble. Calcium carbonate, very weak electrolyte because it's classified as being insoluble. Number 8 is just a covalent compound. Okay, and so it's a non-electrolyte. And then 2, we got sodium right up front, definitely going to be strong just because it's bonded to sodium and it's classified as soluble. And then lead sulfate, a weak electrolyte because it is classified as being insoluble. Okay. Whoa, I kind of rushed through that one, but here you go. Congratulations. One more down. Right, so we got 10, 11, 12, 13, 14, 15, and 16. I'm trying to look at the clock. We're probably going to be doing basically about one chapter per time that we got left. And it should be about right. Maybe we'll be a little bit early because there's a couple of chapters that are very short. You know, maybe 30 minutes. That's how short they are. And so we're probably going to end up with maybe 1, maybe 2, I call them study days at the end of the semester, meaning that I'll be here. There'll be no lecture because we did the lecture, or we've done all the chapters, but I will be here and open to, basically a office visit, and you can come in with any type of questions you have.